Hey everybody, welcome to the Aide Technical Services webinar on basic fuel management and scan data. This is obviously our first webinar. Hopefully this goes good. So what I've done here is I have recorded this session previously and I'm going to monitor the playback. So I'll be live. You can chat with me at any point during the playback on this thing. There should be a chat button in the bottom of your screen. So if you want to send me a message or anything like that, just click on the chat button and I should get it right away. So let's get started here. A quick review of our objectives. We're going to quickly review, maybe not quickly, but we're going to review fuel trim, what it is, how the different fuel control systems affect fuel trim readings. Basically, we're looking at mass airflow and MAF systems or speed density systems, how to use fuel trim to diagnose drivability and emission failures. From there, we're going to move into how to use scan data to determine the failure area. And finally, we've got some case studies that we'll take a look at and go through. So what is fuel trim? Fuel trim basically is the PCM's response to correct any mistakes in the air fuel mixture based on feedback from the oxygen sensor or air fuel ratio sensor. In a nutshell, the computer figures out how much air went into the engine, adds the correct amount of fuel, that air fuel mixture is then combusted, spit out into the exhaust, and the oxygen sensor kind of takes a look at it and see how close the computer did to getting it right. Obviously, if there's a mistake, the computer has to correct it. Now, the correction will show up on your scan tool in one of three ways. So there are three trim values that the PCM uses to correct the fuel mixture. The first one is, or the first two are short and long-term fuel trim, and the second one is rear fuel trim. Rear fuel trim is fairly recent. It's pretty much been there since the onset of OBD2. However, we really haven't been allowed to look at it until recently. So short-term fuel trim is the PCM's immediate response to the oxygen sensor. So whatever the oxygen sensor is doing, fuel trim is responding right away. You can see this on your scan tool. If the PCM detects that the fuel mixture is too rich, short-term fuel trim will lean it out. If the mixture is too lean, short-term fuel trim will come in and richen it up to get the car running back to where it should be. So in this example, this is a scan tool screen taken using, looks like Auto Ingenuity. And all we did here with this car is you can see that the car's in pretty good fuel control through this section. And right here, I just pulled off a vacuum hose. The engine immediately went lean. The computer picked up on it by the oxygen sensor and it started to add fuel right away. Now the thing about this is it's directly reacting. So the O2 or air fuel ratio sensor is directly reacting to the changes in fuel mixture. So almost as quick as I'm trying to trip this car up, the computer is going in and fixing it, which is red in short-term fuel trim. And the same thing happens over here if I create a rich mixture, which I did on this car simply by adding a bit of propane. You can see as soon as I hit it with propane, the computer immediately reacted and fixed the fuel mixture. So here we created a fault rich, and the computer fixed it right away. Negative fuel trim numbers means the fuel mixture is being leaned out, which means your underlying condition is rich, and the exact opposite if the car is lean. Okay. Fuel trim will add fuel to it. So if you've got a fuel trim reading of plus or plus 15 or 16, something like that, the car is lean, so you're looking for a lean condition. Long-term fuel trim, on the other hand, is something entirely different. So long-term fuel trim is monitoring short-term fuel trim to see how it's doing. If short-term fuel trim is out of range, long-term fuel trim will eventually step in and make corrections to get short-term fuel trim back where it should be. Short-term fuel trim is responding to the O2 sensor. Long-term fuel trim is responding to short-term fuel trim. Long-term fuel trim is a more permanent change. So basically what the computer does is when it calculates how much air has entered the engine, it goes to a lookup table, pulls a number as to injector on time, that sort of thing. The fuel is injected, and then the PCM takes a look at it via short-term fuel trim. Well, short-term fuel trim is offside for any length of time. The computer knows that there's something wrong with the formula, so it will literally go in and rewrite the formula a little bit to get the car back on track. And that correction, which is more permanent than short-term, shows up in long-term fuel trim. Long-term fuel trim is permanent unless the PCM's memory is erased. You do a global reset or a keep alive memory reset or something of that nature. Short-term is live, long-term isn't. Long-term is a correction to the computer's operating program. And if you take a look at this example right here, this is a car that's in pretty good fuel control. You can see short-term fuel trim in and around the 0 mark, sort of mirroring what the oxygen sensor would be doing. And then you can see right above that, you can see long-term fuel trim isn't changing. Well, short-term fuel trim is right where it's supposed to be, so there really is no reason for long-term fuel trim to change. Now in this example, what we did was right here, we added some propane to this vehicle. The oxygen sensor picked up on it. Short-term fuel trim went in and started to make corrections, and then long-term fuel trim kind of watched it for a little while, and when it didn't come back, it started to make some changes. So it started to rewrite the program a little bit to, sort of bring short-term fuel trim back up where it was supposed to be. So you see where short-term fuel trim went in the beginning over here. So let me highlight that. So right here is where we created the problem. Right here is where long-term fuel trim started to fix it up. And by the time long-term fuel trim had got the problem fixed up, it wound up kind of where short-term fuel trim started out, and short-term fuel trim is back on track. Now that is a typical response that you would see on just about any car based on what we did to it by adding propane. Okay, to wrap this up, if short-term fuel trim is too far from ideal, long-term fuel trim will step back in and alter the fuel pulse width calculation in the computer to bring short-term fuel trim back to ideal. Short-term fuel trim tells you what's happening now. Long-term fuel trim tells you what's been happening over a longer period of time. So one's historical, one is happening now or in the present. If you're wondering what normal fuel trim values are, short-term fuel trim on a car that's in really good fuel control should be plus or minus about 4% and constantly changing. The reason for the change, it's obviously reacting to the oxygen sensor or air-fuel ratio sensor. Long-term fuel trim plus or minus 10% and stable unless you're changing load or RPM. More on that later. Long-term fuel trim is used to analyze. Short-term fuel trim is used to diagnose. And I'll give you an example of that. A car comes in, it's running short-term fuel trim 3 or 4%. Long-term fuel trim is minus 15. Minus 15 means the computer is subtracting 15% fuel, so the car is rich. So from there, we start to put our diagnostic caps on and we start to figure out or start to think about what's wrong with it. So the first thing we do is we pull the PCB valve out of the valve cover, and we see short-term fuel trim jumps from an average of plus or minus 3 or 4% to a plus 5 or 6%. So we've gone up a couple of points, but that's not enough to shift long-term the 15 or so % we're looking for. So you shove the PCB back into the valve cover, you then go over and you pull the canister purge hose off of it, and all of a sudden short-term fuel trim jumps up to plus 18. So if you know that short-term fuel trim took you to plus 18, you're sitting at minus 15 on long-term fuel trim. When all the corrections are kind of dialed in, you're going to be at around a 3 or 4% correction, which is back where you should be. So in this case, we've got fuel leaking into the system through the canister purge system for whatever reason, loaded canister, doesn't really matter at this point. So to go back to my sort of analogy here, long-term fuel trim is used to analyze, short-term fuel trim is used to diagnose. You kind of get the idea what we're talking about there. And then to add to that, this is called a long-term fuel trim fuel cell lookup table, load map. There's a bunch of different names for it, but basically what it is this is a map with a bunch of different coordinates on it. And in each one of those coordinates or cells, we see a fuel trim correction to the base pulse width calculation that was originally installed in the computer. Now, if you take a look at my map here, we can see that this car is running at 6 grams per second airflow and about 650 RPM. So if I go down to my load range here, that puts me in a light load situation. And on my RPM side of things, that's a low RPM. So where these two meet on my coordinate map, RPM and load, I can see that I've got a plus 2% correction in this particular cell. Now what I'm going to do next is I'm going to drive the car. You can see here that my RPM is up, so that puts me up here somewhere in the RPM scale and over here on the load scale. So when I go to the coordinates, I see that in this particular fuel cell, I have a plus 5% correction, which again, this is normal, but you can see how different load and RPM combinations can hit you or get you into different cells on this load map. And how that plays into your diagnostics is you have to be in the right cell to see the data that you want to see. Or put another way, if a customer has a surge at cruise, you bring the car into the service bay to diagnose it, you can look at the fuel trims in the service bay all day long because you're basically looking at an idle block or an idle cell, and your problem is in a load cell. So the data that you're looking at really isn't relevant to the failure. So in order to see what this car is doing, trim-wise, you're going to have to take it out and drive it into the surge. So the vehicle will fuel differently under different load and RPM ranges, and we're going to use this to our advantage to diagnose fuel control faults. We're basically going to manipulate these fuel cells into different load ranges, and from there we're going to learn how to sort out our different types of failures. Just to kind of give you an idea here of what I'm talking about, or to kind of drive it home, you can see here up top we have long-term fuel trim bank 1 and bank 2 on this V6 engine, and down at the bottom we have mass airflow and throttle position. So you can see that in every time I change the throttle, airflow changes, my long-term fuel trim numbers change, and the reason they're changing isn't because the computer is recalculating, it's changing because this thing is hitting different cells on that load map. So moving on into rear fuel trim, a bunch of different names for it: secondary fuel control, fore and aft oxygen sensor control. And basically what's happening here is rear oxygen sensor readings are being read by the computer. Short-term fuel trim is going to make slight corrections like it always does during steady load and RPM conditions, and then once those corrections are recorded, long-term fuel trim will shift slightly to store any corrections that are being made. Values are stored in keep alive memory, so these are permanent unless you go in and wipe out the keep alive memory by either doing a keep alive memory reset, battery disconnect, or however you want to go about doing that. Now the theory here is pretty simple. The rear oxygen sensor sees exhaust gases that are equilibrated. Now that's kind of a fancy term, and we all sort of know what they're talking about here. If you take a look at the exhaust gases coming out of a catalytic converter, they're pretty stable, as opposed to the oxygen content going into the catalytic converter, which is fluctuating. The stuff coming out the back end of it, due to the catalytic converter process, is pretty stabilized, and that's what they're looking at here. Basically what they're doing here is they're using a somewhat stable rear oxygen sensor voltage to fine-tune the feed gas going into the catalytic converter to increase the efficiency of the catalytic converter. Now, all manufacturers do this. They've been doing it pretty much since the day OBD2 got turned on. They just really haven't told us they were doing it. And when it comes to rear fuel trim, the overall correction is supposed to be very small, limited to 1 or 2%. We typically, if we can see it on a scan tool, 3 to 4% is not unusual. We don't go looking for anything at that point, but if you get a 10 or 12% correction from rear fuel trim, then obviously we've got some problems we need to look after. Now, the overall correction here, 2 to 3%, that would be a correction under normal conditions. However, if there's something wrong with the rear oxygen sensor where it's not reading correctly, which is a fairly common failure on some vehicles, the correction can be much, much larger. In fact, I put in your slideshow here to 20%. I've got an example of this coming up a little bit later where the correction was over 30% and it was actually correcting to the point where the car stalled. So 3 to 4%, kind of your upper limit on rear trim. Anything below that is definitely okay. But if you get much over that and you've got drivability issues, then you need to start looking at that rear oxygen sensor. If the rear oxygen sensor needs to be checked, a couple ways you can do it. You can check the rear O2 sensor monitor in mode 6. And then what I prefer to do is drive the vehicle under load, go to a wide open throttle, and then go to a hard decel. So wide open throttle is pretty easy. When I talk about a hard decel, what you're really trying to do here is get the computer to shut off fuel. So you want to basically let off on the gas and downshift it a gear or two so that you get the thing decelerating hard. That should pump a lot of oxygen through the engine and the catalytic converter. So checking mode 6 for the guys that do it's pretty straightforward. You go in, make sure that the CAT monitor and the O2 monitor have run and there's no codes. And you just go in and look at the mode 6 data, which I've got highlighted here. You can see that our catalyst monitoring bank 2 sensor here has a max value of 0.76. Our guy's scoring a 0.34, so that's a clear pass on this oxygen sensor. Next, I'm going to drive the car, and what you can see here from me driving the car is the front oxygen sensor is switching pretty regularly. Keep in mind this is scan data, not a scope. And the rear oxygen sensor is running in around the 0.4 volt range, and it's steady, which is what we would expect to see. Typically on rear oxygen sensors, we're looking on the lower end, 0.3, 0.4 volts. On the high end, 0.6, 0.7. Most of them will run in there, give or take a little bit. And then we're going to drive the car out onto the road, or sorry, we're going to take the car out. We've already got it on the road, and we're going to perform a wide open throttle acceleration. And if you take a look at what's happening here, the white trace, the front oxygen sensor, pegs immediately, which indicates that we've got lots of fuel. The rear one kind of hangs for a little bit. That's because there's still some oxygen in that catalytic converter that has to be used up. And once it gets used up, the rear one pegs as well. We want to see about 0.9 volts when we do that. And then here comes our hard decel. You can see the front oxygen sensor kind of drops like a rock. That's because the engine immediately went lean. And then the rear one, it kind of hung for a while, and that is a normal reaction. During the wide open throttle run, you basically depleted all the oxygen out of the catalytic converter. So now that you start flooding it with oxygen, it's going to suck up some of that oxygen just like a sponge would. But once the catalytic converter becomes saturated, then the oxygen blasts through, hits the rear oxygen sensor, and it should drop like a rock as well. And what we want to see here is we want to see the voltage on the rear oxygen sensor go under about 0.9. So that's kind of a quick, easy test that you can do while you're road testing the car, trying to figure out what's wrong with it. Obviously, all of this depends on the O2 sensors or the air fuel sensors. So if you have any doubt as to their function, they must be tested or checked before testing any further. If you make a bad decision based on bad O2 or air fuel ratio sensor data, you're going to make mistakes in your diagnosis, and we don't want that. Indicators that the O2 sensors are not correct. Short-term fuel trim is too active. Short-term fuel trim numbers are outside of the normal range. Mode 6 data shows that the sensor is close to the limit. All of these can be an indicator that the sensor needs to be tested properly to determine their operational state. So for example, again here we're going back to mode 6. I've gone in and checked this car. My oxygen sensor monitoring is complete. And then when I look at, let me get a pen up here. When I look at this guy right here, I can see that my minimum value on this switching test is 0.5 volts. This oxygen scored a 0.76, which is a clear pass. Get rid of those. Which is a clear pass, indicating that this oxygen sensor is performing normally. Now, if I'm looking at a pass of 0.5 and my oxygen sensor scoring a 0.55 or a 0.57 or something like that, then I know I'm getting close to the failure limit, and I might want to take a closer look at that oxygen sensor with a scope or something of that nature. Okay. The other thing that we see guys do when it comes to oxygen sensor testing is this sort of thing where they take the oxygen sensors and they graph them out in scan data. So this is scan data. And you can see here I've got two oxygen sensors. The one on the bottom looks to be switching a little bit slower than the one on the top. Now the one on the top, the voltage looks to be a little bit lower than the one on the bottom, and that's because if you take a look at the top one there, I haven't scaled them quite the same. So the voltage ranges that they're both hitting is about the same. It's just I made a mistake when I scaled this screen up. Now, when you look at this, it would be pretty easy to come to the conclusion that the bottom oxygen sensor here is reacting slower than the one on the top. Which if this is all you looked at, you would think, well, I may have a problem with that bottom oxygen sensor. And the problem with looking at it this way is you really don't know what the computer is doing to get the oxygen sensors to do this. So instead of looking at the oxygen sensors to see what's going on, what you really should be doing is looking at fuel trim. So here we've added in fuel trim to the previous screen, and you can see down here on the bottom, this car is in really good fuel control. So I've got a rich oxygen sensor. It went rich over here. The computer started to take away fuel. The oxygen sensor responded. The computer picked up on it, started to add fuel. Oxygen sensor went up. Computer picked on it. The computer started to pull fuel away. Oxygen sensor responded, and you can see that all the way through this trace. On this one, however, you can see that car went lean. The computer added fuel. The oxygen sensor didn't come up before the computer started to pull fuel away. So I've got fuel being pulled away here. The oxygen sensor responds by going down. The computer immediately starts to add fuel. It doesn't see the oxygen sensor come up the way it wants, so it pumped in more fuel. And you can see it does it several times during this test. This is a classic short-term fuel trim correction for an oxygen sensor that's responding too slow. So if you want to look at oxygen sensors and that kind of stuff to see whether they're controlling fuel properly, whether they're fast enough, that kind of stuff, I would suggest you stop looking at oxygen sensors, the oxygen sensor pattern, and shift over and start looking at short-term fuel trim. It tells a much better story. Now, I've got a case study coming up here later on in the program where we'll show you how to test an oxygen sensor with a scope as well. And then sort of the final piece of this puzzle when it comes to fuel trim is the engine management system. The engine management system will dictate how you interpret the fuel trim readings, i.e. whether the car is speed density or mass airflow. Now, both of these systems are radically different in their method of operation or how they go about figuring out how much air is going into the engine. Therefore, both of these systems are going to react quite differently to most faults. To give you an example, this is a speed density system. Now the speed density system uses barometric pressure, engine load, usually from a MAF sensor or something like that, air temperature via an intake air temperature, RPM from crank sensor, and programmed information on the displacement of the engine. So all of these are combined to do a calculation of how much air is going into the engine. Now the thing to keep in mind here is it is a calculation, not an actual measurement. So on speed density systems, for the most part, when it comes to fueling, they don't really care where the air comes from. or looked at another way, MAP for baro and load, crank for RPM, intake air temperature, and programming account for about 95% of the fuel shot. The other stuff, TPS, intake air temperature, engine coolant temperature sensor, accessory loads, that kind of stuff, are all modifiers. They account for maybe 5 to 10% of the fuel shot. So they're not really that influential when it comes to figuring out how much fuel should be injected. When you compare that to a mass airflow meter system, there's an actual air measurement taking place here of how much fuel is being added to the engine. So the difference here is one is calculating, one is measuring. Now, on a mass airflow meter system, they absolutely do care where the fuel comes from. On a mass airflow meter car, all the air entering the engine has to go by the mass airflow meter or the system can't account for it, which typically leads them out. When we look at our injector shot, again, about 90 to 95% of that injector shot is coming from the mass airflow meter and crank sensor. Now everything else, intake air temperature, TPS, ECT, accessory loads, all that kind of stuff become a modifier. The one thing that I don't have here in either diagram is the oxygen sensor or the feedback system. And the reason for that, and I kind of want to make a point of this, the reason for that is the feedback system has nothing to do with this. The feedback system is a totally separate system that the computer uses to fine-tune the fuel shot. It's basically the watchdog here. So the computer is grabbing this information, injecting the fuel, and then it watches the oxygen sensor to see how the burn was, and it will make slight adjustments. So the feedback system is basically the watchdog to make sure that this process is working properly. When it comes to using fuel trim, and now that we have a good understanding of what that is, combining it with the engine management systems that are out there, here we've got two different systems. We've got a speed density on the left, I believe it's a Chrysler minivan, and on the right we've got a mass airflow meter system, I believe it's a Ford pickup, and we created the same fault in both systems. And what we did was we just pulled off a vacuum hose. So over here we created a vacuum leak. On the speed density system, the change in engine load or the change in manifold vacuum was immediately picked up on by the MAF sensor, and the computer made an instant correction to the fueling of the car, so you really don't see a change in fuel trim. Now what did happen on the speed density car was you let more air into it, the computer is going to give it more fuel because of the calculation part of this. Feedback doesn't change, however the engine does speed up. On a car that is non-drive-by-wire, that would be typically a high idle condition or something like that. On a drive-by-wire car, typically what you get is throttle body codes, because the computer has to close the throttle plate further than normal to get the car to idle, so it sets some different kind of codes, and you kind of need to watch that when you're doing your diagnostics. However, on the Ford, when we created the vacuum leak, we let air into the engine that didn't go by the mass airflow meter. So because the mass airflow meter didn't know the air was there, it had no way to adjust for it, and the computer had to add fuel by the feedback system to get the car fuel mixture correct. So same problem, exactly the same problem on two different fuel calculating systems, and we get two totally different results. So you kind of need to bear that in mind when you're troubleshooting these things, because different faults are going to affect different systems in different ways. And I've got some more of that coming up. All faults manifest themselves in some form in fuel trim. Our take on this is that in order to use fuel trim effectively, you must put your failure into one of four categories: fuel delivery faults, engine breathing faults, calculation faults, or feedback faults. If you can kind of slot your failure into one of those four categories, you can figure out very, very quickly what's wrong with the vehicle. Now, generally, to put the car into one of those four categories, you're going to have to manipulate that load map that we talked about earlier, to see what the car does under different conditions. Those conditions include light load. So this is typically a hot, no-load idle. So the car is sitting in park, all the accessories turned off, and you're just looking at sort of idle trims after the car goes into closed loop. Medium load, which is typically cruise, 80 to 100 kilometers an hour going down the road at a steady rate. Flat surface is typically what we're talking about here. And then high load is the engine is under acceleration. It's not quite a wide open throttle, but you're accelerating hard enough to get the car to work pretty much as hard as you can without shoving it into open loop. It's kind of where we put that. Now sometimes, well, not sometimes, most times, we use light load and sort of a, I'm going to call it a 3/4 load, which is somewhere between a medium load and a high load, to do the bulk of our diagnostics. And usually with those two readings, we can fit our failure into one of the categories. So we're going to talk about fuel delivery faults first. The fuel delivery fault is when the fuel delivery system delivers more fuel than the PCM is programmed for. This is quite rare. You don't see this very often. This, on the other hand, is quite common. The fuel delivery system delivers less fuel than the PCM is programmed for. Typically, this would be your plug fuel filters, fuel pumps, power and ground issues to the fuel pump, that sort of thing. And irregardless of which fault you have, the PCM has to compensate with fuel trim to get the correct mixture. Too little fuel on your scan tool typically will show up as normal fuel trim values at idle and light load. That's sort of self-explanatory. At idle and light loads, you don't need much fuel. Therefore, so if you have something wrong with a pump or something like that, it generally has no problem providing enough fuel to idle the engine. However, as you start to load the engine up, the fuel delivery system starts to come up short. The computer picks it up via the oxygen sensor and it starts to add fuel. So your fuel trims start to go positive. And the key here is the more load you add, the further and further positive in fuel trim you're going to go, because the car is literally leaning itself out as you increase the demand for fuel. Too much fuel is kind of the exact opposite. At idle, your fuel trims will tend to be negative because the engine is rich for whatever reason. And then as the demand for fuel goes up, it will get better and better and better. So at medium and high loads, your fuel trim values may be, they actually may come into the normal range depending on what's wrong with it. Now so in this example, we're going to use our load map to show you a fuel delivery fault. So here at light load, our trims are pretty good. In fact, at a total fuel trim correction here of 1%, they're actually perfect. And then at a medium load, we can see a total fuel trim correction here of about 16%, which means the car is lean. It's still running okay, but it's lean. And then at a high load, we're adding about 35% fuel. Total fuel trim. Total fuel trim is nothing more than combining short and long trim together into a single number. But we're 35% lean here. So this engine is leaning out as we load it up and as the demand for fuel increases. So this is a classic case of fuel starvation caused by too little fuel. Fuel delivery faults, I put some typical causes in here: fuel pumps, plug fuel filters, fuel pressure regulators, vacuum hoses, fuel driver modules, power and ground issues to the pump, injector electrical issues, that kind of stuff. All pretty standard stuff, but again, you're going to use your diagnostic to tell you whether you have a fuel delivery problem, and from there, then you're going to start checking this stuff in detail to figure out where the actual problem is. Engine breathing problems include vacuum leaks, restrictions on the intake side, which are very rare, restrictions on the exhaust side, and an imbalance in airflow through an engine on V-type engines or inline engines with dual catalytic converters. So if you take a look at this guy, this is a mass airflow meter car with a vacuum leak. At idle, the airflow is very low because of the throttle plate being closed. So when we let extra air in, it has a fairly large impact on air going into the engine. So this would be a vacuum leak. The engine leans out. Fuel trim compensates for it by adding fuel. Now, all we need to do here to verify that it's a vacuum leak, generally, is just load it up. When we put the car under load, our fuel trim values go back into the normal range. The reason for that, we added more air, the computer added more fuel. The vacuum leak didn't get any bigger, so it had less of an effect on the fuel mixture. So this is a classic vacuum leak sort of scenario on a mass airflow meter system. Keep in mind that a vacuum leak on a speed density system isn't going to really look like this. Exhaust restrictions, I didn't put intake restrictions in here because they're somewhat rare. Exhaust restrictions on a speed density car, typically, depending on how bad it is, unless it's really severe, generally at idle, the car's not moving a lot of air, so any restriction on the exhaust that you have isn't going to have that much of effect, so you can run trim values that are close to normal. However, as you start to move air through the engine, the load is going to be overestimated due to the low vacuum that the engine is producing for a given throttle opening. And what happens then is the computer sees the low vacuum and thinks the engine is under much more load than it is, so it delivers more fuel. Obviously, the oxygen sensor is going to pick it up, and it's going to try and lean the vehicle out. So on a speed density car, an exhaust restriction generally looks like pretty good numbers at idle, but as you start to drive it, you go lean, and the harder you push it, the leaner you get. Or sorry, the more negative you get. On a mass airflow meter car, though, it really doesn't show up in fuel trim the way you think it was or would, because on a mass airflow meter car, even though the car may be down on power, the exhaust may be restricted, the airflow through the mass airflow meter is also reduced, so the computer automatically meters out the right amount of air the right amount of fuel for the air that's going into the engine. So on a mass airflow meter system, typically exhaust restrictions don't tend to bother fuel trim very much. So we have to take a bit of a different look at this thing. So two things you're looking for here is take the car out, drive it under a fairly high load situation, look at the oxygen sensors or air-fuel ratio sensors, and make sure that the car goes full rich. And then take a look at your fuel trims and make sure that they're in the normal range. Now, if the oxygen sensor doesn't go full rich, or your fuel trims are outside of the normal limits, then you've got a different problem. On MAF systems, if fuel trims are normal and the O2 sensor shows full rich under load, then the engine is not breathing. Okay. If, however, the oxygen sensor doesn't go full rich or the fuel trims are abnormal, then it's something else, one of the other categories. Now, I'm going to throw this out there. We've had a couple of rare instances where we ran across this thing, this set of conditions where it goes full rich, fuel trims aren't a problem, and the car won't pull. And I don't know how many cases we've had. It's not very many, but in every one of those cases, the rare cases where it hasn't been a catalytic converter, it's always been ignition timing due to a spun reluctor wheel on the harmonic or on the crankshaft. Okay, 99% of the time, this is going to be an engine problem. That 1%, you may want to check ignition timing with a lab scope. And then the last sort of thing when it comes to airflow is this airflow imbalance. So this is a V engine. It's a Ford, in case you didn't recognize the scan tool. And what I've got is I've got long-term fuel trim bank 1 at minus 13 and long-term fuel trim bank 2 at plus 20, 23. So obviously one bank is rich, bank 1, and one bank is lean, bank 2. Now this car was setting a lean bank 2 trouble code. And your instinct would be to go after bank 2, vacuum leak, fuel delivery, whatever the case may be. The problem is actually on bank 1. Here's kind of how it works. You've got 10 grams of air being sucked into the engine. The mass airflow meter is measuring that. So if the exhaust is not restricted, you can expect 5 grams of air to go to the right bank, 5 grams of air to go to the left bank, or 5 grams to bank 1 and 5 grams to bank 2. So on bank 1, what happens, this is the restricted bank, you get 2 grams of air but fuel for 5. That makes the mixture rich, and the computer has to pull fuel away to get the car or to get that bank to run properly. On the other bank, bank 2, you've got 8 grams of air but only fuel for 5, so that bank tends to look out. Or sorry, that bank tends to lean out. And the computer picks up on that. Now in our particular example here, this guy's setting codes for bank 2 being lean when the problem is actually on bank 1. So as a general rule of thumb here, what you're looking for when you run into this, the bank that is the most positive, okay, the bank that is the most positive is the good bank. In our example here, that would be bank 2. Okay, so that's an airflow imbalance. Calculation error is when the PCM is receiving bad information. This causes the PCM to incorrectly calculate the amount of fuel required. Calculation faults cause fuel trim to be abnormal under all conditions. In all of the other examples that we've shown you so far, except for the airflow imbalance, there is a place where you can get the fuel trims kind of into the normal range. When you have a calculation fault, generally that's not true. You won't be able to get the car into what I would consider those normal fuel trim numbers. And here's an example of a Mazda that had a bad mass airflow meter on it. At idle, we're showing minus 23 on short term. We take the car out, drive it. It doesn't change much. It's still showing lean. Now we know this is not a too high fuel pressure thing, because if it was, when we load it up, that minus 25 should have dropped down to closer to, minus 10, minus 8, something like that. So we know that's not what we're dealing with here. So this is a typical scan data or trim data from a car that has a calculation error. And the last one is a feedback error. Feedback errors are when the fuel trim response is the opposite of what it's supposed to be. Or put another way, the engine is rich and fuel trim is adding fuel. So basically, if it's rich, it should be leaning it out. It's not. It's adding it's adding fuel to an already rich engine. And the same thing on the lean side. If the engine is lean and fuel trim is subtracting fuel, then the car's not thinking straight. In our experience, feedback errors are almost always caused by O2 sensors or air fuel sensor faults. Okay. Now you may have to physically check the sensors, but more often than not, you can easily see it in the scan data. Here's an example of a car that had a stalling issue, and this car wasn't setting any codes. It's a little bit of an older car. I think it's an old Dodge Neon. But if you take a look at the data here, you can see that long and short-term fuel trim is adding about 30% fuel. The front oxygen sensor is pegged at 0.97, which indicates that the engine is extremely rich. And what was happening here, this car kept adding fuel literally until the car stalled. And the reason it's adding fuel is if you look at the rear oxygen sensor, it's sitting at 0 volts. So what the computer's trying to do here is it's trying to use rear fuel trim to get this car to richen up so they can get the catalytic converter back in the sweet spot. And because the rear oxygen sensor on this car is dead, the computer just keeps adding fuel, and literally it keeps adding fuel to the point where the car stalls. So the giveaway here is it's rich, the computer's adding fuel, okay, and then the cause of it down here is that rear oxygen sensor. And then kind of wrapping up this whole fuel trim chart before we get into the case studies, I put two charts in your handout, and they'll also be in this video. And basically what we have here is we have a symptom chart. So you match sort of your fuel trim conditions up on the left here in this row. You load it, that kind of stuff, manipulate the car, do our different load ranges, and then over here you've kind of got what the faults are. Okay, and I've done two charts here, one for MAF sensor cars and one for speed density cars. Again, it's by no means a complete list or anything like that, but it should be enough to kind of get you pointed in the right direction. And then finally, to kind of wrap this up, we're going to run through a couple of case studies here. So the first one is a 2008 Yukon 6-liter. Customer's complaint is check engine lights on, no drivability complaints. This is a couple of years old, so it was back in the time of e-testing. I'm pretty sure if this thing hadn't needed to get a drive clean pass, it would have never, we would have never seen it, because the customer wasn't having any issues with it other than the check engine light is on. And the shop that was working on this thing, it's setting a code 1153, which is insufficient switching bank 2 sensor 1. The shop that was working on this thing had already replaced the bank 2 sensor 1 oxygen sensor. Anyway, we got to it. You can see from the code screen here that this is a current failure. So what we did was we started the vehicle up. We wanted to get it into closed loop to see what was going on. So this is our idle trims. You can see short and long term. A little on the high side, but not excessive. And the car is running in open loop right now, and we know it's in open loop because short-term fuel trim bank 1 and bank 2 not active. So after letting the car run and warm up for a few minutes, we go in, and now we can see it's gone into closed loop. Short-term fuel trim is now active, and if you take a look at short-term fuel trim bank 2, we can see that we're popping up around points, or sorry, we're popping up around 7%. We're hitting that every once in a while, and from our previous discussion, we want short-term fuel trim to be in that 3 or 4% range. So this is a little bit excessive. Now, it's not drastically bad or anything like that. It's not screaming at anything. And bank 1 is a little bit lower at 5%. Again, that's just a little bit outside of the happy range. And neither one of these is a big issue. And if it wasn't for the check engine light, we probably wouldn't even waste too much time investigating this thing. However, it is setting a check engine light, so we need to get it fixed. So the first thing we did was a live plot on short-term fuel trim. And if you take a look at it, you can see here, this is much better looking at it graphically than it is looking at it just as numbers scrolling by, because you can see some things here that you can't. If you take a look at bank 1, which is the thicker of the two white lines here, you can see it's much tighter and it's moving much faster, as opposed to bank 2, which is hitting, it's hitting much higher. It's hitting that 7% or so, and it's not cycling nearly as fast. So the live plot on bank 2 does show some problems. Obviously, the computer's correct in its assessment that there is something wrong with bank 2, or the switching rate on bank 2. And when we go in and look at the oxygen sensors on bank 1 and bank 2, again, the heavy line is the bank 1 sensor. It's way more active than the thin line, which is bank 2. So again, the scan data is kind of backing up what we're seeing on the codes, in that we've got a problem with the way the bank 2 sensor is switching on this thing. Now again, it's not drastic, but it's definitely there, and given the age of the vehicle, it's setting a code. So what we did was we suspected the oxygen sensor, even though it was new. So we went in, and if you're really going to get down to testing oxygen sensors, really the only way to do it is with a lab scope if you want to be 100% sure. Little bit different with air-fuel ratio sensor testing. We have a whole course on that, so look for that in an upcoming webinar, or you can go to our Aide site and look at it there. However, we're in here with the scope now, and what you're seeing here basically is the bottom trace, which is bank 1, is very consistent. It's much faster. It's kind of hitting its voltage levels, that sort of thing. And when we look at bank 2, it's hitting its voltage levels, but it's switching much slower. So we suspected the oxygen sensor. So the first thing we did was we ran a manual test on it. And how you do that is very simple. Basically what you do is you perform several wide open throttle accelerations. So you're wah, 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 and you keep doing that until you get the engine to really respond well and capture one of them like we did here. You can see where we boxed in the capture that we're going to look at. And then over here on the right, we're going to measure how long it takes the oxygen sensor to transition from lean to rich during our snap throttle. And if you take a look at that, our oxygen sensor, the good one, came in at about 62 milliseconds. Same thing with the one that's got the trim issue or the slow issue. It came in at about the same time. So both of these oxygen sensors are performing a lean to rich transition in about 62 milliseconds. Well, the specification on an oxygen sensor to as far as reaction time has been for years 100 milliseconds. So we're clocking in both oxygen sensors at 62 milliseconds. They're well under the 100 millisecond switch point, and all that tells us is whatever's wrong with this thing, it's not the oxygen sensor. Okay. So trims indicate, that the system is calculating properly. Total trims show normal correction of less than 10%. The oxygen sensors do show the slow switch, especially bank 2. And short-term fuel trim is outside of our normal window on bank 2. We saw that. The oxygen sensors are not the problem. We tested them on the snap throttle test, which is the only real 100% valid test on an oxygen sensor. If you're ever in doubt, that is the way to test it. So we had two thoughts here. Number one, we were thinking that this engine may have had some carbon on the intake valves on the bank 2 side, and that when the fuel was being injected, the valves were kind of soaking it up a little bit. That was one thought we had. The second one was the fuel injectors themselves. The fuel injectors were definitely easier to test, so we went with them first. And what you're looking at here is we hooked up a pressure transducer to the fuel rail, and we went with the scan tool and we activated the injectors. And if you take a look at it, I believe these are operated in the firing order, but don't quote me on that. You can see that between the highest flowing injectors, which are two on the left, and the lowest flowing injectors, which are the ones on the right, we've got almost a 2 psi change in pressure drop, which is well outside the normal range. We look for 1 psi max injector to injector, and even that is a bit of a stretch. So a 2 psi or almost 2 psi, there's a fairly large or fairly significant change in fuel flow through these injectors. But the bottom line on this one, it needs the injectors cleaned or replaced, and that's what it took to fix the vehicle. The next one here is a Honda CR-V. It's a 2009. And the customer's complaint on this one was check engine light on, and it ran rough or ran poorly after it warmed up a little bit. When we went in and checked it for codes, it had a 300, 301, 302, 304, 171. There was some issue where the air conditioning compressor does not engage, which we didn't even look at on this car. And this is the code screen we pulled off it. So you can see all 4 cylinders are showing misfires. We've also got a 300, and then we've got the 171 fuel system 2 lean bank 1. Now this is a classic kind of case of, which came first, the chicken or the eggs. did the lean code cause the misfires, or did the misfires cause the lean code? And it's a bit of a toss-up, because if the car is running lean, or if the computer thinks it's lean, it can mess around with the fuel mixture to cause it to misfire. However, if the engine is actually misfiring, that's going to dump a lot of oxygen into the exhaust, which the computer will pick up on and set lean codes. Now, what we did to try and sort this out was basically we wanted to see whether the misfires were there when the car was in open loop, or whether they showed up after, and that would give us a sort of an indicator as to whether the misfires were causing the lean code, or the lean code was causing the misfire. And we suspect that if it was the misfire causing the lean condition, the misfire or the car would run badly right from the get-go, and ours didn't. When we started it up, it ran okay. So this led us to believe that the lean issue was causing the misfire. So if you take a look at the fuel trims here, you can see your commanded lambda. This has got an air fuel ratio sensor in it, is 1. The actual lambda is 1, which is bang on. And our fuel trims here, short term, this is displayed a little bit different. So far we've been using sort of a percentage scale, 0 plus or minus 10. Here they use whole numbers, so 1.00 would be the equivalent of 0. So 0.94 is a little bit less than that. How much less? 6%. So this would be a negative 6% correction on short term, and long-term fuel trim correction would be minus 2% at this particular moment in time, neither of which are glaringly bad. The minus 6% on short term is a little bit outside of our happy window, but it's not enough to upset this car, and at this point it's definitely not causing our condition. We just took the car in, loaded it up a little bit just to see what it would do under load. Short term went from slightly negative to slightly positive. Long term didn't change, and our lambda numbers are stayed in the good range. So we just let the car warm up a little bit more, and what we noticed was the car is now starting to run bad, and we're starting to see some things. If you take a look at the air fuel lambda, the commanded lambda is 1. The actual lambda is 1.06. And if you understand lambda, what it's telling you here is the car is showing 6% lean. However, when I look at fuel trim at 1.21, that means the computer is adding 21% fuel over its normal schedule to try and fix the lean condition. Right? So the computer is picking up on the fact that the car is lean, and the computer is pouring fuel to it to try and richen it up to get rid of the lean issue. Now the car is running, it's not running terrible at this point, but here, a couple of minutes later, it's running quite bad. Now you can see here that we've gone from 21% correction to 47%. The computer still wants lambda 1, and we've got an air fuel ratio, actual air fuel ratio showing on the front air fuel ratio sensor of 23% lean. So here's a situation where the car is reporting it's 23% lean. Short-term fuel trim is showing a 47% fuel add, and the car is rich. It smells rich. It's running like it's rich, and it almost appears like the computer is doling out the fuel, but the air fuel ratio sensor is not picking up on it. So what we're looking for here is verification. Is the car doing what it says it's doing? And if you take a look at the rear oxygen sensor here, the rear oxygen sensor is showing full rich. That would go along with the air fuel ratio sensor, fuel trim showing a 47% fuel add. So the computer says it's adding fuel. The rear sensor agrees with it. The front one, however, does not. The front sensor is still showing lean, even though the car is running rich and the computer is adding fuel to it. So the conclusion here is that front air fuel ratio sensor is faulty. It's faulty to the point where it's fueling the car, or it's fooling the car into adding 47% fuel which is causing the engine to run bad enough that it's being picked up on the misfire counter. Now, interestingly enough, this air fuel ratio sensor is toast, but we don't have codes for the air fuel ratio sensor. So here, without being able to see the trims in the air fuel ratio sensor, we could have made a lot of mistakes chasing down misfires, that kind of stuff. But fuel trim led us, between fuel trim and the air fuel ratio and oxygen sensor readings, it led us to a fairly quick diagnostic on this car, and we were able to find a bad front air fuel ratio sensor on this Honda. Okay. So just to kind of wrap it up, that's our class on basic fuel management and scan data. When we do this class live, it typically runs about 2 hours. Anyway, I hope you enjoyed our inaugural broadcast. We had a couple of glitches, but we got through it okay. And as soon as I get this video rendered and edited, I will send out a link to you guys with the post on it. And thanks for watching. Have a good one.